Welcome back, everybody, to the start of the second week of the semester. Hope everybody's settling in. The first assignment was posted, I think it was actually supposed to come out today, but I thought it was supposed to come out on Friday, so I posted it over the weekend. But you have a week and a half or so to do it. If you do have any questions, you can feel free to email me, make an office hour appointment, or if it's a quick question, you just answer it over email. And again, you're certainly encouraged to work together on that, or use any kind of tools to help solve the problems. Just make sure you write up your own solutions so that we can maintain good academic standards. Okay, so like we always do, I'm going to start off with a little bit of a review. So what did we cover last time? We covered sort of a grab bag of different topics. We started off with some basic ocean geography, sort of looking over the whole globe. Where are the five major ocean basins? Atlantic, Indian, and Pacific, and then Southern and Arctic at the poles. What are their sort of basic properties? And then we looked at where do these oceans actually come from? Starting all the way back at the beginning with the formation of the solar system. The idea was that we had this cloud of nebular gas. The sun formed at the middle. It sort of turned into this disk, and then in that solar disk, we formed that sun, and then planets, protoplanets around the edge of the disk. Once those planets solidify, we have the sort of Earth similar to the form of the Earth today, but the early atmosphere was quite different than today's atmosphere because essentially the atmosphere is formed by gases that are trapped in the Earth when it forms, sort of coming out through volcanic emissions. And those volcanic emissions would have been things like water vapor, CO2 primarily, as opposed to today's atmosphere, which is largely oxygen and nitrogen. And so the idea is we have this primordial atmosphere that fills up with water vapor. When that atmosphere becomes saturated, we rain out, and that forms our early oceans. And then after that, we sort of switched topics and moved on to the idea of the sort of geological processes that actually set the properties of the ocean that we see today. For example, depth, where are the continents, things like that. And this is all traced to this idea called continental drift. I just have a sort of a figure down here about this, where the idea is that in the past, the continents were not in their current locations, but they were all jammed together in this supercontinent called Pangaea, which had this large ocean, Panthalassa, surrounding it. And we sort of got into a varied discussion about what's the evidence for that. There are certain evidences that come from, for example, matching rock formations. So there are rock formations in Newfoundland that are connected to rock formations that are found in the eastern US and also in Scandinavia. And so that sort of signals that all those rocks and those mountain chains were kind of together at one time. But then there was also this glacial evidence that suggested that regions of the Earth which are now tropical, like for example Australia, had evidence that they were in the past glaciated, so they had ice sheets on them. That leaves these marks on the ground, scouring marks when the glaciers advance and retreat. And we're looking for explanations for that. One explanation, of course, is that previously these continents were in different locations. Maybe Australia was polar, and that's how it became glaciated. But there was another idea that we could at least consider, which is global climate change. And that brought us into a discussion of snowball Earth, this idea that in the past, global climate might have been extremely different. And in fact, it's thought that that did indeed occur, although it's not the explanation for these glacial deposits. We talked about some cool evidence for snowball Earth, like these drop stones, which are dropped from the bottom of ice sheets into the open ocean. And our sort of accepted explanation for these is that they were sort of transported to those areas by large global scale ice sheets. And we also talked about what would be the mechanism that drives that kind of global change. And one major mechanism is actually variations in the amount of solar radiation that we receive. Maybe if we get less solar radiation, the Earth will cool down and it'll cause some kind of global climate change. And then there were a few types of solar radiation changes that we discussed. One was the sunspot cycle, which is not a large enough signal to cause global climate change, but you can see small climate changes happening because of that. But another very major one was what we call Milankovitch forcing. And so what Milankovitch forcing is there's these three parameters, eccentricity, obliquity, and precession, that all sort of had to do with sort of small aspects of the Earth's orbit. So the Earth's orbit is mostly circular, but it has small deviations from being a circle. And those things actually fluctuate on 10,000, 50,000, 100,000 year timescales. And that's really believed to cause major climate changes on those orbital timescales, they're called. And then just at the end, we talked about this idea of the ice albedo feedback, and that's where we're going to start today. So just as a reminder, we're talking about where the ocean floor came from, the structures of the ocean basins. There was this idea of continental drift, and then we talked about snowball Earth as sort of a competing mechanism. So the key idea that I want to mention now is that although it's the case that top of atmosphere radiation variations, like changes in the sun or changes in the Earth's orbit, are considered to be the fundamental driver of large-scale, global-scale climate change, they don't act alone, and there are a whole set of physical phenomena that are called climate feedbacks that play a major role in amplifying the relatively small changes in incoming radiation, and they amplify them so we have a bigger effect on global climate, such as freezing the entire surface ocean. And there's all sorts of climate feedbacks, and you could take a whole course on different feedbacks in the climate. And a feedback is essentially it's like an amplifier. So actually, if you play guitar or any kind of music, there's an electrical circuit inside those devices that has a feedback structure that amplifies the signal. And the same sort of general principle operates when we're talking about global climate change. And in the case of snowball Earth, the most important feedback is called the ice albedo feedback. And so it's very simple to understand the basic idea of how it works. So suppose we have, for some reason, the sun we're getting less energy from the sun. Maybe it's because of Blankovich forcing, or maybe it's because of sunspots, or changes in solar evolution. Well, so that's going to cause the climate to cool a little bit. And so once the climate cools, that means that conditions are favorable for growing more ice, whether it's sea ice or whether it's land-based ice like glaciers, than we previously had. And ice, we all know, like from going snowblind here in the wintertime, is much more reflective than the brown earth or green trees or blue ocean. Ice actually reflects, it's called the albedo effect. Ice reflects solar energy back out to space. Now it doesn't reflect it all, some of it is caught by the greenhouse gases and re-radiated back down. But generally when we have more ice and the surface of the Earth looks white instead of blue or green, we reflect incoming solar radiation. So we have cooler climate, develop more ice, we reflect more solar radiation than we previously did, and that means because we're getting less energy, the climate is going to cool more, and then the cycle continues. So when we cool more, we develop more ice, and it doesn't necessarily mean that this process continues infinitely, and any small perturbation leads to total freezing, but this mechanism amplifies reductions in the solar radiation that we receive at the top of the atmosphere, which can occur for various reasons. And so on assignment 1, if anybody has taken a look, there's a question about thinking about this ice albedo feedback, I spelled it wrong, in two cases, one the snowball Earth case, which I just outlined, but also this process can sort of operate in either direction. You can sort of either grow ice or melt ice, and both of them are called the ice albedo feedback, but it can either cause warming or cooling, depending on whether it's operating sort of in the forward direction or in the reverse direction. And so you can ponder this, and there's a sort of a written explanation question on assignment 1. But that was really an aside about sort of competing ideas about how you could glaciate Australia. But we understand today, based on mostly things like carbon dating of rocks, that the real reason for those glacial deposits is actually the continents were in different places, but there's other evidence that supports this ideas of continental drift and plate tectonics. And this is a pretty important picture that I like to keep in mind, which is sort of the just generic cartoon of how plate tectonics work and how continents move. So the overall structure of ocean basins. So here we have the ideas on the right-hand side. This is like a little piece of a continent. So this is an edge of a continent. Then we have an ocean basin in between, maybe some islands. And then underneath, we're showing the upper mantle. So the rocks here, the gray part, that's the crust. So that's the skin of the apple that we all live on and can't drill through. And then the red part is the upper mantle. And the cartoon might be a little bit confusing because it sort of looks like we're floating on magma. That's not the case. These are warmer rocks than the surface rocks, but these are still solid rocks. But a very interesting fact that actually some of the greatest scientists in history didn't understand until the last 100 years or so is that over very, very long time scales, these rocks in the upper mantle actually can move around and convect. And so almost as if they were a fluid, so it's not magma, it's solid rock, but almost as if it were a fluid over very, very long time scales because of the incredible amounts of stress and pressure that the rocks are under, they can actually circulate around. And just like when you're boiling a kettle, that circulation of rocks actually transports heat around, and it transports heat a lot more rapidly than diffusion or just sort of simple conduction of heat through the rocks would carry out. And so I just want to take a minute here and look at the overall structure of this diagram. So we get evidence, strong evidence, for the correctness of this plate tectonics picture just by looking at the features that exist in the ocean basins. And so there are two really important features, and they're called mid-ocean ridges and subduction zones, which probably many of you have seen in a previous course we touched on some geology. So mid-ocean ridges are found essentially at the center, the east-west center, mostly, of ocean basins. And so in the Atlantic, they're called the mid-Atlantic ridges. And these are underwater mountains that are several kilometers high, so they can be about 2,500 meters tall, so very, very tall, that sit on the bottom of the ocean floor. And these places are actually where oceanic crust, or the seafloor itself, is actually created. And they're filled with sort of volcanic rocks like basalts. And there's lots of volcanic activity happening there. We're forming new seafloor. And so what happens at these mid-ocean ridges is that hot material from the upper mantle actually rises to the surface, becomes molten as the pressure drops, and then flows out of essentially volcanic sites that lie all along the center of the ocean basins. And these mid-ocean ridges, they represent a plate boundary. So we'll see shortly a diagram that shows the collection of plates on the Earth's surface. So the crust is essentially broken up into these very large pieces that we call plates, and the plates move relative to one another. And they can either sort of spread apart, called divergence, or they can come together, called convergence. And at the mid-ocean ridges, these are sites where the seafloor is spreading. So the two plates, there's one plate on the eastern side, say, one plate on the western side, and they're moving away from each other. And what that's doing is it's making room for this hot material that's going to come to the surface and form new oceanic crust at the center here. And so what these arrows are showing is kind of like sort of a conveyor belt. These slabs, or this oceanic crust, is flowing away over very long time scales. This is tens and 50 million year time scales, flowing away from the central axis of the mid-ocean ridges. And it flows away typically until it sort of gets to the point where the oceanic crust makes contact with the continental crust. And you can see on the diagram, it's just a cartoon, but the continental crust is quite a bit thicker than the oceanic crust, and it's thicker and it's less dense. And so what happens is, because this continental crust is less dense, it almost sort of floats or sits on top of the oceanic crust, and the oceanic crust does what's called subduction and falls down underneath the continental crust. So we start at the mid-ocean ridges. Over millions and millions of years, we move from the center to the edges of the basin, and then we have subduction happening where the plate, which is called the descending slab now, falls down. We have this relatively cold slab that's descending, subducting underneath the continental crust. And then once this oceanic crust gets down into the upper mantle, it sort of becomes integrated and recycled into the upper mantle. And at the places where this oceanic crust meets the continental crust, we then have these deep trenches. And these happen at the edges of ocean basins. We'll see a specific example with the Pacific now shortly. But these deep trenches are some of the deepest areas of the ocean floor. And for example, the Mariana Trench is a site of one of these subduction zones. And so we have mid-ocean ridges in the middle. That's where seafloor is generated. Seafloor is destroyed at the edges in subduction zones, which are deep trenches. And underneath all of this, it's being supported by large-scale, very large-scale convection and sort of thermally driven circulations that are happening in the upper mantle, which again is made out of solid rocks that are moving very, very slowly and not actually hot magma, except at the point where the seafloor is actually being formed and mid-ocean ridges. And so this cartoon is a very good one to keep in mind, and you sort of don't really need to understand plate tectonics at any more sophisticated level than this, but just understanding these two main features, seafloor spreading of mid-ocean ridges, and subduction and recycling of crust at subduction zones and trenches. This is the idea. Okay, so I'm now going to shortly show some really compelling evidence that's direct observational evidence for that simple cartoon, but it's going to involve measuring the age of the ocean floor. So in the 1960s, there was a fairly substantial deep sea drilling survey where resources were made available mostly from the US government, I think maybe the Navy, and they were trying to survey all the ocean bathymetry, and as they went around they took lots of samples, and they were measuring how old were the rocks on the sea floor. And so I have some hint here on the slide, but can anyone just give a quick comment on how generally do we date rocks? Does anyone know, or they've had a course, or maybe they've even done it? Yes?
Isotopes typically?
Yeah, isotopes, and roughly, and you don't have, if you're not sure, so roughly speaking, how does that work? Or
seeing, I think, the amount of a certain carbon isotope in a sample.
Right, and that changes over time?
Yes.
And why does it change over time?
With half-life.
Half-life, exactly, which has to do with radioactive decay, right? So essentially, there's different isotopes, which are basically, if you take an element, like we're going to talk about the periodic table later, take an element on the periodic table, it has a certain number of protons, that same number of electrons, but the number of neutrons in those elements can vary. Those are called different isotopes. And some of those are unstable, and they decay over time at some very well-known rate. And we can detect or measure how much of what's called the parent nucleus is there compared to I think they're normally called the daughter nucleus. And by looking at those ratios, we can say how long has it been decaying for. And so this is kind of an example. We have some unstable nucleus at the top, and it emits particles, and then it changes down through various decay reactions. And we measure the ratios of these various components, and that can tell us how long the decay process has been happening. But it sort of raises a fundamental question that sort of puzzled me actually when I first started teaching this course, which is, what does it mean, the age of a rock? Like, what does that actually mean? Like, obviously the elements of the rock have existed, I guess, forever, since the salt was formed in the sun. So does anyone know, or has anyone considered this question? When we say a rock is a certain age, like what does that actually mean? It's been a certain amount of time since something happened. Anyone have an idea? It wasn't obvious to me.
Since it probably cooled from a magma.
Cooled from magma, so that's exactly what I thought, and that's very close, that's almost exactly right. But it's actually not exactly when it's solidified, although that's the right idea. So it does have to do with cooling, but not specifically the solidification. But what it has to do with is when the rock cools to a particular temperature, which is specific to each type of rock, called the closure temperature. And so the idea is when the rocks are very hot, even if they're solid, you can essentially have random diffusion, like random motions of these isotopes that can escape. If you have a particular micro grain of a rock, in order to do this isotope analysis, you need to assume it's a closed system. So none of the isotopes are leaving or coming in from other nearby grains. And that's true underneath this closure temperature. And so at that point, it's sort of a closed system, and you can make a clean estimate of the ages. So it's very closely related to solidification, and it has that to do with that concept of cooling, but the closure temperature is really the key idea. Okay, so that's what the age of a rock is, and we started looking at them mostly in the 1960s. And then here is a map of what the ocean floor ages actually looks like based on those kinds of measurements. And there's really one feature that jumps out immediately, to my eye at least, which is if we look in the North Atlantic and South Atlantic basins, there's this red stripe that runs symmetrically right down sort of the north-south axis of the Atlantic Ocean. And those bright red colors mean young crust, only a couple million years, whereas the dark brown colors at the edges are about 200 million years. And so this is totally consistent with that plate tectonics cartoon I was showing, because right at these mid-ocean ridge sites, you have upwelling hot magma that's forming brand new oceanic crust, getting cooled below that closure temperature. And so that's why we see very, very young crust that has just been born in the center of the basins. And then that oceanic crust over time rides on that conveyor belt and moves towards the edges of the basins. And as it moves, so what that means is as we move laterally away from those centers, we're seeing older and older crust, which has actually moved to get there from the mid-ocean ridges. And so as we move away from that center up to the northwest Atlantic, or in the Pacific, it's even more spectacular. So we go from the Pacific, mid-Pacific ridge, which is more on the eastern side, all the way over to the western side, northwest. And that's where we get the oldest oceanic crust on the Earth's surface. And that's about 200 million years old. And it's basically just about to be subducted and recycled, maybe in the next 100 million years. So this is really compelling evidence. If you just saw this map, you could almost come up with plate tectonics on your own if you saw this. But that idea actually was anticipated much earlier before, based on this idea that South America and Africa kind of fit together. So sort of a bit of scientific brilliance there. But there's one other general point that I want to make, just about the numbers. So obviously at the center of the mid-ocean ridge is just born, so it's 0 years old, or a couple million, not very old. But it's very interesting how old the oldest crust is. And it turns out it's about 200 million years, and those seafloor rocks are actually much, much younger. Even the oldest seafloor rocks are much, much younger than the continental rocks we find. So you can find continental rocks which are up to about 4 billion years old, which is getting to the actual age of the Earth. It's in the sort of the neighborhood. So continental rocks are just generally much, much older than the rocks on the ocean floor. And this has to do with this idea of the continental crust being less dense. And so as the subduction is occurring at these mid-ocean, ocean trenches, it's the oceanic crust that subducts. This crust is going to subduct in this direction and go underneath this sort of Asian plate and be recycled. But the continental crust continues to float on top because it's less dense. And so the whole ocean sea floor is actually recycled. The entire sort of ocean floor kind of resets itself on hundreds of millions of year timescales. But as far as we can tell, that just doesn't happen to continental rocks, and they kind of just float there forever, and they're gradually rearranged every few hundred million years by plate tectonics and continental drift. Okay, so probably some of that was a review, or maybe you'd encountered before. And now we're going to switch topics, so we're going to completely change and talk about water and seawater and the properties of those. And we're heading towards, we're going to start with fresh water and just understand the molecular structure of water itself, H2O. And then we're moving towards a description of what the actual ocean water looks like in terms of its geographical variability, salinity, things like that. But we're just going to start with fresh water, just sort of set the stage. So it turns out, when understanding oceanography, and it's also true of climate and meteorology, actually looking at the molecular and atomic structure of various molecules, particles, compounds that are involved in the climate system has lots of important effects. So we'll probably touch on this later, but we all know about the greenhouse effect, which warms the planet. The greenhouse effect is essentially entirely based on quantum properties of gas molecules like carbon dioxide that live in the atmosphere. And water vapor is also a potent greenhouse gas, as is methane. So just as a quick reminder, so the basic structure of an atom is we have the nucleus in the center, so that's where the protons and neutrons live, the sort of heavier subatomic particles. And then the electrons, which are equal in number to the protons, so that the overall atom is neutrally electrically charged, exist kind of in a cloud circulating around that nucleus. And you kind of think of them as orbiting around. Really, there's sort of a probability cloud if you think about things quantum mechanically. But we have protons, electrons, and neutrons. The electrons on the outside, this sort of very, very light negatively charged particles, they stick around. They're bound to this nucleus because the nucleus is positively charged and the electrons are negatively charged, and opposite charges attract, so the electrons continue hovering around the nucleus. Understanding what holds the nucleus together, like why does it not just drift apart or fly apart, was a more recent understanding. I think this is understood in the 60s and 70s, which has to do with this force called the strong force. The particles that are carried that strong force is actually called gluons because they glue those nucleons together. It's just an interesting question that I like to ask, which is, if we look at the periodic table, so each element, like for example hydrogen, has one proton, one electron. Helium has 2 protons, 2 electrons. And then there's a whole list of different elements that all have different properties. And there's a few hundred of these elements. Does anyone have an idea, like, have we discovered all the elements? Or are there maybe some we haven't discovered? Or how do we know? Or how many elements should there be? Has anyone ever thought about this question? Like, why are the elements the way that they are? Anyone have an idea or a guess? Or any comment?
Sorry. Is it like, it's based on the amount of protons and electrons like balanced, and like there could be more because there is certain like stable points, I think they're called, where like they're more stable and like the numbers end up working out to make it exist better, but like in order to get to that point, with like particle accelerators and stuff, like certain elements that get created last for like literally like 0.0 seconds.
That's exactly
yeah.
right. Yeah, that's a great answer. So I think when you were talking about stability regions, I think you were talking, there's this word called islands of stability.
Yes, yeah.
And so the whole idea is some configurations. So you could, in principle, just jam together protons and neutrons in a ball and have some electrons there also. And as long as you had protons, neutrons, and a bunch of electrons, that is technically some kind of element or some structure that you might expect to be an element. But some of these configurations turn out to be stable, meaning if you set them up, they will hold together for some amount of time. And others are unstable, meaning they break apart or decay almost immediately, very, very small amounts of time. And so you can imagine if we're trying to detect an element and say, okay, we definitely know iron exists. Where's iron? Here we go. Then if it only exists for 10 to the minus 10 seconds, then it's hard to even measure or detect that. And essentially it's thought that we actually haven't discovered all of the elements yet, but we've discovered almost all of them. And there may be configurations that are beyond what we have in the periodic table, that are stable for small amounts of time, but it all has to do with this notion of stability. And we're actually going to come back to this idea later, because stability is a very general concept in physics, which is if you put something together, will it blow apart spontaneously almost immediately, or will it kind of hang out and be comfortable in that configuration? And you can think about stability in terms of ocean currents and eddies and waves and that kind of thing, or all the way down to atomic configurations. And so it's just sort of want to bring in that idea early, that how permanent is something? How long will it exist if sort of left unperturbed? It's sort of a fundamental question that arises in all areas of physics. Okay, so let's look at the water molecule, which all the elements, we know them well. So water molecule is H2O, so we have 2 hydrogens, 1 oxygen. And it's a covalent bond between the hydrogen and oxygen, meaning they're sharing electron pairs. And it has this shape that's called a tetrahedral shape. So essentially, we have oxygen in the center, and then we have 2 hydrogens sticking off. And then there are also, and it's almost like it's kind of like a pyramidal shape. And then there are also 2 objects on these other 2 upper sides. So we have 2, so it kind of looks like a pyramid like that. And we have sort of 2 hydrogens on the lower sides. And of course, it can all be rotated anyway. And then 2 things that are called lone pairs on the other side of the oxygen atom. And because of this structure, we have 2 hydrogen atoms and then 2 lone pairs. If you forget about the electrons, then we end up getting this OH shape, which is bent. So unlike a molecule like carbon dioxide, which is a linear molecule, so all the atoms are in a row, water has this bent shape. That's due to the underlying tetrahedral shape with 2 lone pairs. And even the angle between the 2 hydrogens is very well measured. It's about 105 degrees. And this turns out to have very, very important implications, the atomic structure, or molecular structure, I should say, for how the water molecules actually behave. And the reason for that is tied to this property called electronegativity. So when we all took high school or first year chemistry, you probably came across the idea that some atoms, especially fluorine, oxygen, and nitrogen, are more electronegative than other elements, meaning that when they're engaged in a covalent bond, they tend to hoard the electrons closer to themselves. So because oxygen here is electronegative, the electrons sort of like to hang around closer to the oxygen, and so we develop negative charges close to the oxygen. And then because the electrons aren't near the hydrogens, that means the protons are there with their positive charges, and so we develop sort of not a full charge, but a partial positive charge on the two hydrogens. And this means that water is called a polar molecule. And can anyone suggest what's a reason why water being polar is really important? Does anyone have maybe seen this in another course or have an idea? Why is the polarity very, very critical? There's something that water does all the time that other, yes?
Because it allows it to be like a universal solvent, so it can like mix with other.
That's right. So it's basically the determining factor in the fact that water is the sort of a great solvent. But even underlying that, the sort of physical reason that it is a great solvent has to do with this thing called hydrogen bonds that probably people have encountered before. So because water is polar, we said here yes. So why is it important? And then the answer here is hydrogen bonding. So this is a diagram now that's showing, just like what I drew on the boards, we have the oxygen atom is in red. That develops a negative charge because it's electronegative. The two hydrogens get a little positive charge. And now because there's little charges, so it's the whole atom, the whole molecule is electrically neutral, but it has locally in space weak positive and negative charges. And that means that those molecules, you have several water molecules around, they can arrange themselves in a way where the pluses on the hydrogens on one water molecule are close to the negatives on the oxygen on neighboring water molecules. And this leads to an electrical attraction between those two neighboring molecules, and that basically helps water sort of stick together. So it makes it have cohesion. It influences a number of properties of water, like it has a high surface tension. It's a great solvent because it allows polar molecules to fit into the structure, and it affects things like heat capacities and latent heats, which we're going to talk now in a moment in more detail. So hydrogen bonding is essentially so the main reason that the polar aspect or property of water molecules is so important is that it leads to hydrogen bonding, which is just a hugely important property of water. So we talked about this. This was actually mentioned. So why is water such a good solvent? And particularly if we think about water dissolving something like salt. So we're going to talk lots and lots about salt in this course. It's very, very important to oceanography. But if you imagine having sodium chloride, so this is NaCl here, this is an idea, but if this was a crystal of sodium chloride, it would look something like this. The negatively charged chloride ions and the positively charged sodium ions are sort of arranged together in this lattice like this, and it makes a cubicle style salt crystal. And now if we put this thing in water, essentially all these positives and negatives, you can put them into a structure of liquid water in such a way that it's electrically favorable, meaning everything likes to stick together. And so for the negative chloride ions, you can imagine sticking a bunch of waters around them with the plus sides pointing in. So we have a nice electrically bound system here. And so meaning electrically bound, what I mean is it would be hard to pull it apart because there's electrical stickiness happening there. And likewise, for the positively charged sodium ions, you flip the situation around and you have the negative side of the oxygen near that positively charged ion. And this also sort of likes to stick together. So when we take this salt and we put it in a huge amount of water molecules, these ions get broken apart and they exist in these things called, I think they're called hydration clouds of molecules that are electrostatically stuck because of the positive and negative charge attractions all around those two ions. And so this immediately suggests an idea that water can dissolve salt very well, but we all know, so what can water not dissolve very well? What's a commonplace example?
Oil.
Oil. And the reason is why?
Because of the polarity?
Because of the polarity. So in particular, oil is not polar. So oil generally is just a whole bunch of carbon atoms, more or less, all stuck together in these really long chains, called hydrocarbons. And that is very, very symmetrical. So the electrons are all sort of evenly distributed. There's no overall charge. And so if you try to put oil in water, it doesn't like existing in this sea of charges and kind of gets repelled to the surface. So that's why if you pour olive oil into water, it will separate in this coherent layer. So oil is a nonpolar substance, and so it's not soluble in water. Okay, so we've already sort of discussed this question, at least one aspect of it. But so water has all these very interesting properties. It's a hugely complex molecule in terms of its behavior. And so in particular, obviously on the Earth's surface, water exists in all three major states of matter: water vapor in the air, liquid water in the oceans, and solid water ice in glaciers and sea ice and so forth. So the question I want to ask is, what holds water together in the solid and liquid state? So in the gas state, all the molecules are kind of flying around randomly. They're not really directly connected. But in water or in liquid water or in solid ice, they stay together and they move relative to each other a little bit, but they mostly stick together. So what causes those solid and liquid states? Why is water not always a gas with all the molecules moving independently? Anyone have an idea? One idea we've already talked about. Yes?
Intermolecular forces.
Right, so the different molecules in water, they actually attract each other. And what are some examples of the intermolecular forces? There's various types, and I want to know what are some of them. So we talked about one already. Yes?
London dispersion forces is one.
Yes, so they're which are also called van der Waals forces. Yeah, so I'm going to talk about van der Waals forces. So that's van der Waals forces, and then hydrogen bonding is another one, because in the ice structure, for example, in liquid water, hydrogen bonds help those water molecules sort of stick together. Those are quite strong. But actually, you might ask them, well, if it's just hydrogen bonds, why does any other liquid happen that doesn't have, solid, like liquid gasoline, which is all hydrocarbons? Why is that a liquid? The reason is because there's different categories of intermolecular forces. Hydrogen bonds are very important for water, but there's another category called van der Waals forces. They're also called London dispersion. And these are weak, attractive interactions between molecules that happen when the molecules are very, very close to one another. And you can understand there's a really cool mechanism for why these molecules would stick together. I actually learned this from, I didn't actually learn this when I was a physics student. I learned it taking a first-year biology class that was taught by one of the main organizers of the Human Genome Project. So he explained that there's a sort of a very conceptual, simple picture that you can use to understand why would two neutral molecules that are next to each other, why would they attract each other in these van der Waals forces? And the key thing to think about is that the molecules or the atoms are basically made of a nucleus in the center, and then there's an electron cloud around that center. So the nucleus is red, and the electron cloud here is teal. But because of essentially quantum mechanical fluctuations, or you can think of it as sort of the random sort of movement of the electrons around this nucleus, that electron cloud is not always in the same place. It sort of exhibits quantum mechanical fluctuations, so it's sort of fluctuating around. And so at any given moment, you might observe this particle and see that rather than the cloud being totally spherically symmetric, it might have sort of bulged out along the equator, or any random direction, and contracted a little bit along the side. So when you do that, if you concentrate the electrons, say in the eastern and western sides, you get a negative charge there temporarily. This is just a random event. And anomalous, like little partial positive charges on the sides. And this is just happening all the time randomly. And then we can consider what would happen if, instead of having one molecule that was exhibiting these kinds of random fluctuations, we actually had two neighboring ones. So let's take our molecule or atom that's exhibiting a random fluctuation like this, and put another unperturbed atom next to it. So if we think about what's going to happen to this one now, it has this initial spherically symmetric cloud, but now there's a negative charge that's a little bit stronger than it ought to be, quite close to it. And what that's going to do is bring the positive charges, I guess it's going to push away the negative charges, and it's going to induce, in this neighboring molecule, a polarization like this, where there's a positive charge that sort of comes to the surface here, that's attracted to that negative charge, and then the negative charges are pushed off to the opposite poles. And so this is called an induced polarization. So you have one atom or molecule that's undergoing sort of random fluctuations, but then because those fluctuations exist, it induces a polarization in a nearby molecule. And now if we look at this, we have plus on one side and minus on the other side next to each other. So we develop basically a spontaneously organized electrostatic attraction. So what these van der Waals forces, London dispersion forces, really are is the induction in neighboring water molecules of polarizations that lead to an electrical attraction. And fundamentally, there's sort of quantum mechanical fluctuations underlying the whole process. Okay, so we have these, so that's intermolecular forces that are holding liquid water together. It's van der Waals, and then also hydrogen bonds. But if you have enough energy, you can break all those bonds. You can break the van der Waals attraction, break the hydrogen bonds, and you can change the structure of water. And so we exist in these three phases. So on the left-hand side, we here have water ice. Water ice has this hexagonal, sort of hexagon structures where everything is lined up to take advantage of the hydrogen bonds. And in ice, these molecules are kind of vibrating in place, but they're not really moving much relative to each other other than vibrations. Then in the liquid stage, we've broken some of these bonds so that now the water molecules can move relative to one another. But even in liquid water, there are arrangements in sort of molecular level structures where molecules are still arranged in a pattern that takes advantage of hydrogen bonds. But then when we get all the way to water vapor, gas, the molecules all essentially move independently. So to get to this point, you have to start from ice or start from liquid water, and then put in enough energy to rip all these bonds apart, and then we have high energy water molecules flying around in the gas phase. And of course, because of these hydrogen bonds, because water is so cohesive and likes to stick together, you have to put in quite a bit of energy to reach those liquid and gas states. And that really is shown in these diagrams. So the left diagram is showing the melting point and boiling point of water. So the melting point is where you transition from ice to liquid water, and then the boiling point is transitioning from liquid water to steam or water vapor. And if we look at what temperature in Celsius degrees does the water have to be raised to, the ice have to be raised to before it melts, it's 0 degrees. But if you think about the melting point of something like carbon dioxide, it's a bit funny to think about that because we often think about carbon dioxide as a gas, but dry ice is actually solid carbon dioxide, which melts at about minus 90 or somewhere maybe even colder than that. And so other similar compounds by similar amount of similar weight, similar triatomic, they melt at a much lower temperature, so it's easier to melt them. And also the boiling point of water is very high, 100 degrees, but many other similar compounds would actually transition all the way to the vapor phase in the negative temperatures, minus 70 or so. So the melting and boiling points of water are hugely higher than other similar compounds, and this has to do with the water's stickiness. Because of hydrogen bonds and these van der Waals, it likes to stick together, and it's hard to rip the molecules apart. And that's also reflected in the heat capacity. So you'll have a chance to play around with this on the first assignment. But the heat capacity basically is, if I put a certain amount of energy into a sample of water, how much does the temperature go up? The heat capacity of water is it's kind of like the opposite of that. How slowly does the heat temperature go up when I add energy? And water has this very high heat capacity compared to something like metal, iron, or silicates have a much lower heat capacity, meaning when you add energy to them, they warm up very, very quickly. But water, you have to put in lots and lots of energy to get the temperature to budge. The reason for this, essentially, is that you can think of the temperature of some substance, like sort of a liquid, for example. The temperature really has to do with how fast the molecules in that liquid are moving at the molecular level. It's the definition of temperature, if you do more physics, has to do with the kinetic energy of the molecules that make up that substance. And as a sort of a mental model, I like to think of all materials, whether it's solid or liquid, maybe not so much gas, as molecules that are connected by all these little springs. And when you have hydrogen bonds in the system, the hydrogen bonds are like all these extra springs that get added. So there's extra little springs that are tying the molecules together, which have to do with these little plus and minus charges and the arrangement of the atoms in space. So when you have all these little springs, that's called having extra degrees of freedom. So there's essentially more ways for the system to oscillate because there are all these extra springs. And the degrees of freedom of a substance are directly connected. There's whole bits of thermodynamics and statistical mechanics courses on this. The more degrees of freedom you have, the higher heat capacity. So essentially, because we have hydrogen bonds, there's all these extra springs between these molecules, and that leads to it being very efficient at absorbing heat without changing its temperature very much. Okay, so the next topic we're going to cover is latent heat and how we transition between different phases of matter. But we're almost out of time, so I think we've covered plenty, so I'm going to leave that for today. So I will see everybody on Wednesday. And at this point, we've covered a good amount of the material for the assignment, so you can feel free to take a look. We still have plenty of time. And feel free to let me know if you have any questions. Other than that, I will see everybody on Wednesday.
Hi. So about the reference letters.
Oh, yes.
Yeah, I think there's an explanation.
Did you see the email that Denise sent?
Yeah, and after you sent your email to me, they sent another one. I think it's a whole email to everyone. It's like, this is the deadline, you need to put your reference on it.
Okay.
Yeah, something like that. And this is the main question. We need to add our reference names and their emails.
Right.
Automatically, they send an email to the reference with the
Okay.
letter. So, this is my question. The deadline is 18.
Yeah.
So, you see this?
Actually, can we talk about this in a minute? Because there's a few students who, yeah. Maybe we can just talk about it. Just let me look at my schedule real quick. I actually have a break between now and 1, so can we just, you want to talk to my office after this, and we can just chat for a few minutes?
Okay.
Okay. How's it going?
Pretty good. How's it going to be?
Also good.
Right, so I have a question regarding the ice albedo
Oh, sure, yeah.
cycle. So you said that it has the potential to go both forward and backward.
That's right.
So I'm wondering what the critical point is. What would cause the cycle to switch direction?
So what causes the cycle to switch direction is what the initial forcing is. So essentially, if you initially have, say, an increase in top of atmosphere radiation, then that means that you're going to melt ice. And then when you melt ice more, you have less reflection, right? So that's a sort of a positive warming cycle.
So stuff like.
But if you have a cold anomaly at the top, so you have maybe Milankovitch or something, or the Earth gets a little bit further away, or the sun gets weaker, well, then you form more ice. So it doesn't have to do with the state of the system. What it has to do with is what's the input signal. And the ice albedo feedback will amplify either warming or cooling. But it just makes the climate system, we often talk about, and I'll talk about it probably late in the course, there's this concept called climate sensitivity, which is if we add so much CO2 or we add so much extra radiation, how much temperature change are we going to get? And all these various feedbacks, including ice albedo, and then there's numerous other feedbacks, they amplify the signal, and it'll amplify either plus or minus.
So solar winds are critical, like one of the external factors influencing the.
Yeah, the external factors is the changes in the orbit of the planet, changes in solar cycles, sunspots, changes in solar evolution, greenhouse gases, all those things could change the amount of radiation we get.
Okay, all right.
Okay.
Thank you.
Excellent.
Hey, I'm just a little confused about the assignment because we haven't been given any equations. Are we
Right.
supposed to just know them, or?
So, you want to step around? So I'll bring up the assignment.
Sure.
So that's true. And what you will often find in this course is that I don't put a lot of emphasis on teaching specific formulas. There's some we will, but most of the formulas that you'll need for the first assignment are actually given in the questions.
Okay.
So, or they're basic things like, so something that I would expect, or not necessarily expect, but you can look it up or whatever, is, for example, the density of something is equal to mass over volume. So
Right.
you've probably seen that formula before, right?
Yeah.
So in the first question, for example, what am I saying? I'm saying you know the depth of the ocean and you know the area. So what you would need to do is, if you want to know the area of the ocean, you need to take 71% of the area of the Earth's surface. But I'm giving you the Earth's radius,
Okay.
and then the area is 4 pi r squared, the area of the surface of the sphere.
Okay.
So the area of the ocean would be 71% times the area of the Earth, and then the volume of the ocean would equal the area of the ocean times the depth.
Okay.
So you just sort of think of it as a big cube or rectangular prism or whatever. And then if you know, for example, the density, so I'm telling you the density of the ocean is 1025
kilograms per meter cubed. The extra little bit, the 25, that's because of the salt. Normally it would be 1,000, but because it's salty, it's 1025.
Okay.
And so if you want so one question is calculate the mass of the ocean. So the mass of the ocean, from this formula, you cross multiply by volume here, is going to be equal to the density of the ocean, multiplied by the volume, which is the same as the density, times the area, times the depth.
Okay.
So when you see a problem where there's no formula explicitly given, now later on I do give you a formula. For example, I say, for example, pressure is force over area, and I think later on I talk about latent heat, and I say the formula for latent heat is Q, which is the heat, equals the mass times the latent heat, and I give you the values. That was what we were going to cover. We'll cover that on Wednesday.
Okay.
But so very often, if there's not a particular formula from the notes, it's probably either something geometrical, like just a volume or an area or something, or it's on the problem sheet.
Okay.
And if you are stuck, this kind of question is totally fine, because I could maybe forget to put it or whatever. So, but yeah.
Okay.
But there will be lots of stuff on the assignments that isn't directly from the classes, because I like to use the assignments to do sort of a lot of big picture calculations, like how much water is in the atmosphere or whatever. It would be kind of laborious to do it in class. It's a fun exercise to do it on your own. But yeah, a lot of the times the formulas are probably like, if it's not there, if the formula's not there, it's probably a simpler problem than you might even be thinking. Just something like this.
Perfect. Can I take a picture of that?
I'll go right back.
It's been a couple of years since I did physics, so
Yeah,
that's why
that's true of many people that take this course.
Perfect.
Thank you.
So,
So I actually missed the last classes because I had residency surgery, so I missed out like on the syllabus, but I did go through all the lecture notes
sure.
and everything. I just had a question regarding like the exams format. Is it gonna be like the assignments? Like the questions in the assignment, will there be like diagrams?
yes, so the midterms and the final are going to be something like about half of it is multiple choice. So things like, we talked about today, isoalbedo feedback. So like which feedback would be involved in creating snowball Earth, and it'd be different options, something like that. And then some of it will be either written explanations or maybe like label a diagram. Like here's a diagram from the notes. You label in like which one is whatever, like which one is the, later on we're going to talk about seasons, for example. So which one is the summer solstice and which one is the winter, whatever. So there'll be diagram labeling, and then usually about 20% is some kind of physics type calculation. And the physics type calculations will be very similar to what you get in the assignments.
Okay, perfect. I have one last question. So for the assignments, you just want us to like submit in like a Word document?
So you can do whatever you want. So what most people do is they actually just write it up by hand and they submit a photo, and that's fine. If you want to type it up, that's great, but you don't. That usually is laborious, so you don't need to do that. The one thing is, if you're writing it up and taking a photo, try to make the photo like decently high quality and try to have your writing be legible. But yeah, you can submit in whatever form you want.
Perfect. Thank you.
Excellent.